Hey everyone, welcome back. Today we are diving into the fascinating world of concurrency and deadlock in operating systems. Understanding how operating systems handle multiple processes running at the same time is key to knowing how our computers work smoothly, or sometimes not so smoothly. Let's explore how concurrency works, what deadlock is, and how operating systems manage these challenges. Let's start with concurrency. Concurrency is essentially the ability of an operating system to execute multiple processes or threads seemingly at the same time. This is a big deal in modern computing. Imagine trying to open a web browser, listen to music, and type in a document all at once. Concurrency is what makes this multitasking possible. Underneath, your CPU is rapidly switching between these tasks, creating the illusion that all of them are happening simultaneously. This switching is known as context switching, where the CPU saves the state of one task and loses the state of another. It happens so quickly that we hardly notice it. To make multitasking even more efficient, most programs are designed with threads. A thread is the smallest unit of processing in a program, and each thread can handle a different part of a task. For instance, one thread in a browser might be fetching data from a server, while another handles displaying the web page. Multithreading or running multiple threads within the same process allows this task to run concurrently, making programs faster and more responsive. But concurrency isn't perfect. When multiple threads are accessing the same resources like a file, memory, space, or printer, they can clash. This is where race conditions come into play. A race condition occurs when two or more threads try to access and modify shared data at the same time, leading to unexpected outcomes. To prevent these issues, operating systems use techniques like locks, semaphores, and mutexes to control access to resources. These mechanisms ensure that only one thread can access a resource at a time, preventing conflicts and maintaining data integrity. However, they also introduce their own challenges, like deadlock, which we will get into next. So, what exactly is deadlock? Deadlock is a situation where two or more processes are stuck waiting for each other to release resources, resulting in a standstill. Imagine two cars facing each other on a narrow road, each waiting for the other to move. Neither car can go forward, creating a deadlock. In an operating system, deadlock can occur when two or more processes hold the resources the other needs to complete their tasks. Each process waits indefinitely, and as a result, none of them can proceed. Deadlock requires four specific conditions, known as the Kaufman conditions. Number 1. Mutual exclusion. Resources can only be used by one process at a time. Number 2. Hold and wait. Processes holding resources can request additional resources. Number 3. No preemption. Resources cannot be forcibly taken away from a process. Number 4. Circular wait. There exists a cycle of processes, each waiting for a resource held by the next in the cycle. If all four of these conditions are met, deadlocks can occur. Understanding this helps in designing systems that can detect or prevent deadlock situations. Operating systems employ various strategies to prevent or handle deadlocks. Here are a few common methods. Number 1. Deadlock prevention. This method breaks one of the Kaufman conditions to prevent a deadlock from occurring in the first place. For instance, by allowing preemption, we could prevent the no preemption condition from being met. Number 2. Deadlock avoidance. Some systems use algorithms like Banker's algorithm to allocate resources safely. The algorithm checks if resources can be allocated without leading to deadlock before proceeding. Number 3. Deadlock detection and recovery. In some cases, deadlock might be allowed to occur, but the system periodically checks for it. If deadlock is detected, the operating system can recover by terminating or restarting processes. Each approach has its pros and cons. Prevention techniques can be restrictive and reduce efficiency, while detection and recovery may introduce overhead and complexity. The operating system's job is to strike a balance, ensuring that processes can run smoothly without unnecessary delays or conflicts. Concurrency and deadlock might sound theoretical, but they have practical impacts on how programs run and respond. A well-managed system lets multiple processes and threads work together harmoniously, creating a seamless experience. But when things go wrong, like a race condition or deadlock, our systems slow down, freeze, or even crash. As developers, understanding concurrency and deadlock is essential because it helps us write more robust and efficient code. Knowing how an operating system handles multiple processes also gives insight into optimizing performance, especially in multi-threaded applications. So, this is a high-level overview of concurrency and deadlock. We covered how operating systems handle multiple processes, the role of threads and synchronization, what deadlock is, and how it can be managed. Understanding these concepts is essential for anyone getting started with operating systems or software development in general. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell so you don't miss any future videos. Thanks for watching, and I will see you in the next one, inshallah. Assalamu alaikum.